Okay, with that, it is time to start. So good afternoon, everyone. Welcome to the session. Welcome to the section of the course, Frequency Domain Dynamics. So in this section, we'll be looking at analyzing our dynamic situation. So looking at a process unit or some aspect of the chemical process, and we are looking at understanding the states of that space. So we are trying to understand all the things that can go on with that unit or with that process. And once we can understand that, we can develop a controller around that. So if you have some unit, so this is, I guess, supposed to be a reactor, and you would like to know how to create the controller in here, then we need to know what sorts of things can go on in this reactor. So does the temperature tend to run away? Is the reaction tending to cause depressurization? So whatever's going on in here, are we able to figure out all those possibilities? And are we able to create a control strategy around those possibilities? And that's quite an open-ended question, because how do we know what sorts of things are going to happen in that reactor? So it's kind of an open problem, and I think I've forgotten to share screen there. So I was pointing around here. So this is, of course, referring to the first set of notes. So we're trying to understand all the things that can go on inside this reactor. And once we can do that, we can develop a control strategy around that. So that, I guess, introduces the concept of this section of the course. And maybe to introduce myself, well, I think I've seen most of you in the earlier courses in the program, right? So you may have seen me in the reactor engineering courses. So that's my area of research, originally at least. So I've been working on mathematical modeling of reactor systems and developing controls around them and so on. So we've run a number of projects on the research side for Sasol and well, various industries. So reaction engineering, you'll see quite a few examples like that, because I like to draw off from the research side of things as well. Okay, so that's introducing the problem, that's introducing me. Obviously, you've all met each other. So maybe just to reflect on the first part of the course, yeah, maybe you can tell me, in the first part of the course, you've all got some good experience with looking at the state of a system and of a process and so on. So you've been developing the unsteady state model of a process and of a unit in the first part of the course, right? So so what we are looking to do is, number one, we know that the processes we are going to deal with look like this, right? So we've got some unit. Let's talk about one unit for now. So we've got some unit, and there exist some states in these unit, in this unit, that matters to us. So for example, if this is a reactor, then the concentration in the reactor and the temperature in the reactor, those are the sorts of things that we want to control. And to exert control on those types of states, we typically do it with streams. So in chemical engineering, it's all about the streams, right? That's one thing we can easily control. We can stick a flow controller on a stream, and we can raise or lower the flow rate. Well, that depends on whether you've got enough pressure behind the stream to raise it, of course. But that, if you like, that's what it comes down to in chemical engineering. We can change the flow rate on a stream, and then that's how we try to control what's happening in the space. So we can control the temperature and pressure and concentration by controlling the flow rates on the streams coming in. And so there are many ways to do that. There are many ways to change our flow rate in the streams, and so we can do that through control. We can figure out what strategy to use to change those flow rates using the controllers that we want to develop here. Okay, I'm just going to shift you off to the side. And so we want to start out with some description of our chemical process. So we are typically interested in some set of states. So typically y is a vector of variables. And as we said, it might be temperature, concentration, pressure, whatever states, whatever variables in here that represent the operation of that unit. That's what we consider the y's. And then the u's are the control, the manipulated variables. So we can change the flow rate here. So u might be the flow rate into that reactor. So we can apply different values for u until we get the y values that we want, right? So if we have a nice equation like this, then we can figure out what u values to plug in to get reasonable values for y. And in fact, this is where our control strategy is going to sit, right? So we want to develop a controller which will tell us how to change u. So we can think about blasting u up and down and trying to control y, but we want to be more intelligent than that. We want to say, okay, for u, it's actually a function in time that we want to create. And in fact, let's emphasize that. So I'm just going to make a kind of sketch pad here. So we've got dy dt is some function of y and u. And these are all time functions. So that's what I wanted to emphasize. All this is obviously changing in time. And so what we really have is, let's use some primitive sketching methods here. Okay, so what we have is in time, we are going to propose that we change u in some way. So let's say we propose to use a sine wave for u. So u might be the inlet flow rate or something like that. So let's say we just decide, right? And we are free to do that. We are free to choose how u is going to change with time. And then we want to understand, if we go and do that, what's going to happen with our signal. So in terms of the behavior or the response from y, how is that going to respond? So is it going to do this? Or is it going to do this? Or, yeah, so what's the response as we use different inputs to the system? Okay, so that's, and of course we could just go ahead and simulate this equation and figure that out, but we don't always have this equation, right? We sometimes only have a few measurements about the process, so we don't know the relationship among these variables. So these are all the types of things that we are trying to unpack here. Now, a kind of complication that we are concerned about is that there doesn't seem to be much limit on the kind of freedom of the system, right? So let's just draw again here. And let's say we have two state variables. Let's say we have temperature and pressure. So let's say the temperature was changing in this way. And let's say the pressure was changing in this way. And they affect each other, we know that, right? Generally speaking, the states affect each other. But there's no constraint if we look at it like this. There's no restriction that this variable could change in this way and this other variable could change in that way. So we are now expected to design a controller in the face of the fact that all these states may change in any particular way. You know, any time function, it looks to us at the moment, it looks like any time function can apply. And so if we start here instead of there, it might be a totally different response. If we start here, you might get something else. And then of course, you've got the corresponding changes in the other variable as well. So it starts to look like a big mess to us, right? It starts to look like there's no chance that you can create a general controller here, right? That's the problem that we have, that the space looks like it's completely free to change as it likes, and yet we are trying to propose a controller which is going to always control our process, no matter what's going on inside there. Okay, maybe just to pause there, any questions or comments? Okay, so we are expected to develop this controller that's going to manage our unit all the time. And what we can do first of all is think about whether it's really the case that everything is as free and easy as this, right? Let's think about whether our space is a bit more constrained. So let's see. So let's think about having two state variables. So let's say we've got y1. Oops. So let's say we've got state variable y1 and another state variable y2. And we are being controlled by u, and we have, of course, the real time t. And maybe let's make it a bit more physical. Let's say this was the total concentration in a reactor, and y2 was the pressure, and u was the inlet flow rate q in. And of course, real time is real time. So now we can think about, if we were observing this reactor, what sorts of traces could we get? Right, so there's our little reactor. Here's our flow rate. We're trying to control this reactor through the flow rate. And now let's just sketch what responses we might get. So on one day, we might start out with the concentration at this value and the temperature is at this value. And let's say it's an exothermic reaction. So as the components react and get consumed, then the temperature rises. So let's say the temperature is rising in this way. And then let's say on another day, we start here instead. And so the concentration was a bit higher. So, so that starts to happen. And then let's say it just so happened that our temperature started out at, let's say, this lower value. So this would rise faster a bit because you have a higher reaction rate and so on. So we've got these types of, so this is situation 1, this is situation 2, and then again 1 and 2 here. So we've got all these scenarios that we could simulate. And now we want to know, how can we learn something general about this process? So there's a way to construct our state variables, or rather the relationship among our state variables. So you see, when we plot it in this usual way, using time, we don't really see the relationships with variables. We almost see them as independent things. We are seeing this concentration is changing here and that temperature is changing there. We don't really see the relationships between them. But there's a different way to view these things, right? Let's imagine taking time slices. So I'm taking one time instant there, another time instant there, and so on. And then what we are going to do here is create what's called a Poincare map. So Poincare was the French mathematician who came up with this. So here's y1, here's y2. And now we can construct the locus of points that tells us about this relationship. So let's say we look at situation 1 at this time instant. So this is T1, let's say. So in the concentration, it's that value. And then in the temperature, it's that value, right? So that defines a point here. So that's y2, so it's a bit further along. So maybe here. And so that defines a point. So the single point tells us both what concentration and temperature are, what the values are. And then if you go over to the next time instant, then you've got a value here and a value here, right? So remember, it must be the same situation that we are talking about, right? So situation 1. So we might get another point here. Right, so we can draw, so we can keep doing that for all these time instants. And so we can get a curve out, and maybe that curve eventually looks like this. So please note, this is not a function. It's not like here with y against t. With y against t, you can't loop back like that. But with y1 against y2, it could turn out to be that while y2 is increasing, then after a while y2 starts decreasing and y1 starts decreasing, and so the curve can curl in like this. So when we look at this Poincare map, it's not the same as plotting a function, right? Here we are showing relationships between variables. So for situation 1, right? Remember now, we said on day 1, we started with this temperature and this concentration. So we had those two curves. And so we ended up getting this curve here. Then on day 2, we started differently. We started at this concentration and this temperature. And so you can go and find time instance. And by the way, we're plotting them from the same T0. So maybe we started at 8 o'clock on day 1 and we got this trace. And then we started at 8 o'clock on day 2. And now we'll get a different trace if we do the same thing. So it might look like that. Right, so when you plot it this way using a Poincare map, then you start to see relationships among the variables. And we have here in the notes a nice example. So this is the function dx dt equals, and then the right-hand side is a polynomial in x and y. And then the other equation is dy dt, and that's another polynomial in x and y. So those are two related variables, dx dt, dy dt. And then if you go ahead and you integrate these two equations, then that will give you some time profiles, right? You can plot x and y against t, and you'll get some curves here. And then you go and take time instance, and then you'll be able to create the locus of points here. So here we are plotting, down here is x, and over here is y. And so we are constructing the locus of all these points here. And you see now that the situation is different. Well, the situation is not different, but our understanding is different now. It's no longer looking like anything can happen. Right here, when you look at it against time, it looks like anything can happen. You've got no hope that another day you could start here and that one could start there. And these initial values could be completely independent. We could start this reactor at one temperature today and any other random temperature tomorrow, and similarly for concentration. So there's no constraint on where you can start here. And so it starts to feel like anything could happen. Any curves could develop here. Whereas now, when you plot it this way, you start to realize, well, actually, it's just a plane of possibilities. So if you pick a point on this plane, then that tells you, okay, if you are at this point where the temperature is this value and that value, then your system will tend to move in this direction. And so you see now we have this nice plane that covers all possibilities. So everything that's possible in this situation is now represented on this set of axes. Okay, so now we can start saying, okay, well, now I can see maybe I could control this process, because when I look at this picture, I can start to think about features on this graph that I want to avoid. So for example, let's say the X value was temperature, right? And of course, we know our equipment will fail if we go past a certain temperature. So maybe the value of 3 is the value where this equipment is going to fail. So you know clearly we never want to end up on any of these curves because they're going to push us out to failure here. It looks like we only want to operate inside of this zone. We only want to start in regions around here, let's say. So that's what we want to understand from this picture, right? We want to create a picture with all the curves shown. And you see these little arrows, that means something, right? So if you pick a point here, that's going to define an X and a Y value. And then you could stick in that X and Y value here on the right-hand side. And that's going to give you dx dt and dy dt. So you've picked a point, and now at that point, you've got dx dt and dy dt. So you can draw as the x component here of this vector, you can draw dx dt, and then you can draw dy dt. So using dx dt and dy dt as components of a vector, you now have a little arrow that tells you the tendency of your system to change. So you've started at this point. You can see now the system is tending to push you in this direction if you start here. So that's why this picture is so valuable and so useful, right? You can almost immediately see how the system will tend to change. And you see, it's extremely easy to generate this picture. You don't even need to integrate anything. You can just create a grid of values. You can say, okay, I want concentrations 0, 10, 20, 30, 40. I want temperatures 200, 220, 240, up to 500. And so you create a set of points here, a set of points there. And then you just stick in each value of each point here. So you pick a point here, 20 and 300. And so you stick in for x20 and for y300. And you just make those substitutions for each point. And so you'll have a vector for every point on this plane. So that means you can just look at this plane and almost immediately figure out where the system is going to end up. Because you can imagine drawing a little, let's say you pick a point here. Okay, let's pick one on the line. You pick a point here. You can see, okay, the system is tending to move in this direction. So you step forward a little bit. You step here. Okay, now it's moving a bit more horizontally to the left. Okay, let's move a bit there. Let's move there. And so you keep going until you figure out where the system goes along those lines. Okay, so do you all get that? These are the Poincare maps. Any questions or comments on that? And maybe I should say by this point, I do expect you to speak in class and question and argue as much as possible. So we want to have a good discussion here, right? This is not a passive sort of just listening to me droning on here, right? So so you've got here this. You've got this Poincare map, so you've got the vectors, and then if you choose to integrate if you choose to specify an initial condition, then you can get the curve, you can integrate it, and you can plot the integration result on here. And now when we look at this map, we can see that there are some interesting features here. You can see, number one, that there's a point here, which is what we call a repulsor. So you see that when you start near this point, the system tends to run away from this point. Can you see that from this point, all the trajectories lead away from it? So this is a point, in a sense, that the system doesn't like. The system tends to push you away from this point. So you start out at this temperature and concentration, the system is definitely going to push you away from there. So this is the opposite. In a sense, it's the opposite of your current, of what might be your current understanding of steady state. You think of steady state as a stable thing where you get to steady state and everything lives happily. Well, this is also a steady state, but this is what we call an unstable steady state. If you sit exactly on the steady state, you will continue on that steady state. You will stay on that steady state. But the moment there's a slight movement away from that, the moment your system is disturbed slightly, the system will quickly push you away from that steady state. So that's what we call unstable steady state. And then here you can see all these orbits are leading back into this steady state. So this is what we call a stable steady state. So if you start at some point away from it, you'll eventually fall into that steady state. It's not the only steady state. These two are not the only steady states. There is another steady state down here. So you can see that if you start here, then the system will loop around and it will fall into this steady state. If you start even closer, it will still loop around, fall into this steady state. But the moment you cross a boundary here, suddenly the system no longer looks for this steady state. Suddenly the system loops around here and then falls into a steady state in here. So actually, in what looked like originally a completely free and open space, we can see that there are just 3 steady states of the system. And there's a kind of boundary here where if you cross this boundary, you are going to fall into this steady state. If you are on the outside of this boundary, no matter where you start, you are going to end up falling into this steady state. So there are two attractor steady states and one repulsor steady state. And so out of all the places you can start, you will eventually end up on one of these two steady states, right? So that's the kind of hidden feature here. So originally it looked like anything could happen. We had no chance of designing a controller. But now we can see if we look at our equations just slightly differently, we can find features, we can find little clues about how the system is actually eventually going to behave. And sometimes we can shift this picture. We can design a controller that actually changes the way this looks. Sometimes the behavior that the system wants to go into is the behavior that we don't want. So even though you've got this nice stable steady state, it's nice from a stability perspective, but these might be undesirable points. Maybe you get bad conversion in your reactor, something like that. And even though this is an unpleasant place to operate, this might be a much better reaction rate for you. So we want to design a controller to navigate this plane. We want to be able to say, I want to stay here, and for the system to stay there. So that's in principle what we are doing. And the way we'll do that is using this field of frequency domain dynamics. Okay, so that's kind of just introducing the field. This is a picture from my own research. So this had to do with the bioleaching of chalcopyrite. And here's the time picture. And this is something the minerals industry reported for many years, that no matter where they started, they always seem to end up on the same steady state. And then on certain odd occasions, they've seemed to fall down into some other steady state. And when you construct the Poincare map for this, you find actually that there are three steady states, and there are two attractor steady states. So you can easily see the two attractor steady states. And then you've got a repulsor steady state here. So if you stayed exactly on that, you would, but the moment the system was disturbed in any way, it would fall to one of these steady states. So the trick here is, if you want to stay up here, you must always make sure you are up just above the steady state. Then the system will do the rest of the work and go there. If you are just below it, it will fall down in this direction. Right, so that's what we're trying to do here. We're trying to understand those features on our system. And then once we understand the features, then we'll know what sorts of controllers to put in place and so on. Okay, so this is just trying to give us a sense of scale and some ideas of the types of pumps. Well, these are more lab scale flow controllers rather than industry scale. So you can read all this stuff. And then taking control action, we'll talk about this in more detail as we go later in the course, but you can think about what's called bang-bang control. So for example, if you think about a light switch in a room, so throughout the day, the intensity of light changes as the sun exposure changes. And then there comes a point where it's too dark and then you just have to switch on the lights. So bang, you switched it to one state using a light. And then when the sunlight is good enough again, then you switch off the light. So a two-state situation, on or off, right? Bang, bang control. Then proportional controllers are a bit different. That might be like the dimmer switch. So you change the control action proportional to how far you are away from your set point. So you want to be at a certain set point. There must be a certain light intensity in the room. Your current situation is different to that. And so you want to apply enough lighting so that you get to your desired amount of light in the room. So there's a certain error that your current environment is away from your desired set point. And so you apply a control action that's proportional to that difference. So the greater the difference from the set point, the more control action you want to take, the more lighting you want to apply. So that's a proportional controller, proportional to the error away from the set point. And then you can talk about proportional integral. So you can say, well, I tried to apply lighting, but the room still stayed dark. So, and as time is going on, it's still staying dark. So I want to apply control action that's proportional to the amount of time. Also, if I look at the history of how long I've been in the darkness, I want to try harder and harder the longer it goes on without light being applied. So that's the way to read this, right? Your error integrated in time tells you how persistent that error is. So if you like, the control action is proportional to the persistence of the error, right? If you are integrating the error, then that's an indication of the persistence of the error, right? And then PID, proportional integral derivative controllers, that's where you also use the derivative of the error. So you say, well, I don't want to wait for the error to happen. If I'm seeing that my state is moving away from my set point, right, then I can work out the derivative and say, well, before you go too far away, let me try and jump ahead of that and control my way out of it. So in a sense, a derivative is trying to predict when you are moving away from the set point. So you try to be predictive and control yourself before you go out of control there. Okay, so anyway, we'll talk about PID controllers in more detail as we go. Any questions or comments so far? Okay.
Hi, sir.
Hi.
If you don't mind, can we please go through example 3?
Example 3 is which one?
Page 7.
Okay. 7. Okay, so I guess this is a follow-on example for so level control in a tank. So it says here we've got level control in a tank through inlet flow control. Okay, so this is the follow-on from example 2, which I think is a follow-on from example 1. Okay, so you've got your tank fed with A and B. Let's just make a sketch. So a tank is fed with A and B, and it's perfectly mixed, and you've got an exit flow as well. Perfectly mixed, and there's an exit stream here. Q out. And I guess this is Q in. And okay, so the vessel has a volume V. That might not be the actual volume of the liquid there. If it is liquid, it doesn't really say. Okay, so you can identify state variables. So a state variable might be the level in the tank. So H, it might be something else like the concentration of the species, Ca and Cb. And so on. You can think of other state variables. Okay, so you can develop the mass balances and so on. So you are looking at, for example, 3. So 3 possible actuators for maintaining a constant concentration of A. So if you want to maintain a constant concentration of A, if you look at this situation, it doesn't say that it's reacting. In fact, it looks trivial in this case because if you are feeding in just one stream of A and B, and you are only withdrawing them also, if there's no reaction here, then the concentration is not going to change. The level may be changing, but the concentration is not going to change for this process. So in this situation, there's actually no control action needed at all. Now, let's think about the situation where that's not the case. So 3 possible actuators. In other words, what are the things you could do to keep a concentration constant? So let's say we had another stream that was entering here as well. And let's say we couldn't control the stream. And let's say this contains some diluent C. And so let's just call that Q2. So there's some flow of C in here, and then that's as C concentration changes, then that's going to change the concentration of A in the space. So you can apply a sensor here. So let's say if you do something like some online detection method so that you are constantly monitoring the concentration of A in here, then you would, so whatever sensor that is, so there's some transmitter here, which is relaying the concentration of A. And then we are wanting to apply a control action here. So a control action here. And then we send that signal out here. So that's going to control the flow rate in the stream here. So depending on the concentration of A here in your controller, this is going to receive a set point of A as well. So let's just call that A set point. So this controller is going to compare the A set point with the A actual. So there's a measurement here of A. It will compare A set point and A actual. And then it will tell the controller, I need more of the stream to enter or less of the stream until I reduce the error. So when we talked about the PID controllers, you might apply a PID strategy here. That's not the only one, but anyway, so you apply some strategy, and then that tells this controller what action to take to try and maintain that concentration. Was that the part of the example you were looking at?
Yes, sir. Okay. Thank you.
Right. Okay, so we'll see further examples like that. And yeah, you can simulate it as well. So you can write the material balance for the situation, and yeah, you can apply the control action and see if you can get to that specific value. Okay. So then coming here. So these are ways to represent the control action again. And now implementing a real controller. So here it's talking about the need to figure out what these parameters are. Right, so we can say in principle, yes, we want the control action to be proportional to the error, but then we need to know how much action to take on this. So typically the units are different here to begin with, right? Let's say it's temperature we are trying to control. So this value will be in temperature, and then the control action is some flow rate most of the time. So the units are different. So we need to figure out how to translate between a temperature difference and a flow rate. And so towards that, we can recognize that there's some significant work to do to get the controller parameter. So there exist these parameters. So we can define the approach PID or whatever it is, but then there will be parameters that we have to tune. And that's where the majority of our work is going to sit. We have to figure out how to set the parameters of the controller so that we actually achieve control. And the reason for these being derivatives and so on, we'll talk about as we go. Okay, so this first set of notes is just a kind of background about real time and so on. It's not yet about frequency domain dynamics. So this just reminds us, yes, there's the real time domain, That's actually what we're controlling. And now, and we can develop equations that describe that real world situation. Now, what we are going to do next is change gears a bit and go back to some very basic stuff in maths. So Laplace transformations. So we met Laplace transformations in differential equation analysis. And in fact, that's exactly what we're doing now. So those material balances we talked about, those are basically differential equations. And of course, in the majority of the chemical engineering you've seen so far, we were trying to avoid differential equations. Almost always we were saying, okay, steady state, steady state, steady state. And now we are saying in controls, things are definitely changing in time. So no more steady state. So now we have everything changing in time. And so now we have to try and figure our way around this time issue. And one of the main things that will happen when we're working in time is that things are going to happen at a certain frequency, right? It's not just that your process is going to go this, go and do this and blah, that's it, right? I changed today exponentially and that's what happened. In reality, what's happening in industry is more like this, right? It's seesawing around all the time, right? Things are just constantly doing this. And then the poor controllers have to try and manage it. And so you've got that going on. So this part of the process is doing this, this other part is doing that. And so it's just constantly happening like this. And so you see, you have to kind of think differently here, that now it's about whole profiles in time that's just jumping up and down all the time. And so instead of trying to also jump up and down around this, we can now try and think, well, is there a frequency behind this, right? If you look at this, yes, there is a kind of frequency. You can see, and you can see multiple frequencies here. So here you can see kind of wider frequencies, right? Well, that's rotten English. You can see lower frequencies here. So there's more for time period here. And you can see higher frequencies here. So you've got things jumping around and the same signal may show different frequencies in it, right? So it's going through cycles. There are many cycles happening all the time, and the cycles sometimes have different frequencies. And we would like to understand how much of the time is it jumping up and down at high frequency? How much of the time is it jumping up and down at a low frequency? And a useful way to do that is with the Laplace transformation. And it looks, almost nonsensibly simple, right? You've got Laplace transformation of some function is equal to the integral, and that's from the lower limit of 0 and the upper limit on infinity. And that's going to be e to the power minus st, where s is a complex number. And then there's your function in t. And we'll see later on that for s, we are often going to use s equals I omega. And now you're thinking, well, this now why make it so mysterious, right? What's the point of going into the complex domain? So we go to the complex domain because we've got this useful Euler's expansion. So if you think back to your Euler's expansion, that tells us that e to the minus I omega t is equal to cos of omega t plus I sine of omega t, right? So when we create our Laplace transform and we stick in this complex number, we are getting this. So you can see a cos function. Maybe let's not worry about the sine side as yet. So we have a cos function here. And so we can think about varying omega. So as we vary omega, we expose our function to different cosines. So, and of course, then we are going to multiply it by f here. So let's think about what's going to happen when you do that. So let's say we apply a cos function like this. I have to try and draw it as if it's one. You know, I had a much better tablet and I could draw directly on. Now I'm like an idiot pulling this mouse here. But anyway, now you see here, if you think about multiplying these two functions together. So I'm going to take this function and I'm going to take this red function and I'm going to multiply them together. And then I'm going to integrate those two things, right? So you multiply each value and you'll get a certain function and then you'll integrate it. Now, in the regions where this function is similar to this function, right? And by similar, I mean similar frequency, right? You can see here, you can say the frequency here is similar to this frequency. Then the functions won't destroy each other. Maybe it's easier to explain why these will destroy each other. Let's take here, right? If you take this zone, your cos function is approximately constant, right? It's not changing as much. So you are taking a function that looks like this, and you are multiplying it with another function which is doing this, right? It's just scissoring around. So if you think about what's going to happen here, you are going to get values plus, minus, plus, minus, plus, minus. So when you integrate this thing, right, if you integrate all this, you are going to get a 0, right? In other words, when the frequencies don't match, then this is going to integrate out to 0, right? Just because you are adding up plus and minus, plus, values that cancel each other out. Whereas when the frequencies are similar, then your functions will look like this. Let's say it's one like that and one like that. Then when you integrate this, the product of these two functions, it's going to be biased on one side. Maybe if this is 0, then this might be -1 or something, right? On average. So when you integrate this, this is going to be some not 0 number. So that tells us that when we do this, when we multiply this cos function by this real function, by this measurement function, and we integrate in time, it's going to give us back one number, and the size of that number tells us how often that function had this frequency, right? Remember, when the function is not similar to this frequency, then it's the result is close to 0. So the values where the frequencies are not the same will be approximately 0. Whereas the values that are similar in frequency, those will tend to survive that integration. So in other words, we are able for a single frequency to get a number which tells us how often we were at that frequency. So it tells us how often were you when things were jumping around at 50 per minute, then you were there maybe 20% of your time, right? So let's say frequency was, what did I say, 50 per minute? And then you figured out, well, I was there 20% of the time. My system was 20% of the time, it was jumping around at 50 per minute, 50 jumps per minute. And you see, then you can change omega to another value. So you can try 80 per minute, and then you figure out, okay, it was 15% of the time, close to 80 per minute. So that's what this is going to do for us, right? The Laplace transformation is going to give us a way to get a number that tells us how often we were close to a particular frequency. So obviously we are going to apply lots of different frequencies in here, and we are going to create a nice curve And that curve is going to tell us, okay, let's try it again. So here's frequency, and maybe let's just say number of times we were at that frequency. So it's going to give us some distribution in frequency. And then we'll be able to say, well, my system is jumping around this frequency and around this frequency. That's really valuable information, right? You can imagine we want to create our controller. So we want to know how often is this process jumping around. And then you can say, well, on average, it jumps around at 120 per minute. And then you can start thinking about putting in a controller. Is that clear? Any questions or comments on that? Okay, so Laplace transformations, and this is basic stuff, but we'll do a quick revision of this. Would you like to do the revision now or take a 10-minute break? So I'll take that to mean we are all very keen on continuing with Laplace transforms. So let's look at this. Just introduces the notion of an operator. So an operator here, using the square brackets, will operate on a function. So this operator alpha operating on the function f will return the square of f plus 1. And then here you can define any kind of operation. So you can define x cubed plus 5 and so on. But this is what we call a nonlinear operator. You can see you've got the cube of x here. You can also have a linear operator. So a linear operator will have the property that if you stick in the sum of two functions which are weighted by constants, then you can get the same result that you get from this if you take the constant times the operation on one of the functions plus the other constant times the operation on that other function. So that's a linear operator. Right, so just absorb this carefully. So alpha is a thing that operates on a function. Now we can take a linear combination of two functions, and then if you take alpha operating on each function in turn, weighted by the constants in the corresponding positions, then you get the same result, right? So that's a linear operation. Right, in a way, it looks obvious, alpha times this and alpha times that. But of course, you can't say alpha times this because alpha is a function. It's a function of a function here. So it's not multiplication. So this is not a linear operator. If you take alpha on x cubed, right, and then alpha on 5, you won't get the same result as this. So that's not a linear operator. And you might think, well, then must all linear operators look like this? It looks like just this to the power 1. Well, you've got the Laplace operator, which looks like this. This looks nonlinear, if you like, but actually this turns out to be linear. So if you, let's see, where did we do that? So the Laplace transform is a linear operator. I know it's here somewhere. Okay. Well, you can try out if you apply a function g. Maybe let's try and do it here. So if you take the Laplace of a times f plus b times g, and that's going to equal the integral, and I'm not going to show the limits there, of e to the minus st times A times F plus B times G, and then that's going to equal, and well, in a way it's kind of obvious here because you can see you can just separate these two, so you can rewrite this as two different integrals. So you can write you can write this plus this, so this is B times G, and then you can take the constant out here in front, A times the integral of that plus B times the integral of that. So this is A times this plus B times that, which is nothing but the Laplace transform of this is the Laplace transform of F, and this is the Laplace transform of G. Right, so that's a quick, easy proof that this the Laplace operator is a linear operator. And that's important because there are certain properties of linear operators which are quite useful. Okay, a couple of other things that are quite useful for all the Laplace operations. Right, you can treat S as a constant of this integration. So if you ever get an S in here, even though we know S is this mysterious complex number, it's still not a function of time. And this integral is in time. Remember, we are trying to integrate to get the frequencies, so we're integrating in time. So S is independent of t. So when you have an S in here and you are integrating, you can remove that S as a constant of time. And then the other thing, just to remember in general, your integral of the product of two functions is, so one of the functions you treat, so if you define one to be f, then the integral of the product of two functions is f integral g minus the integral of ddx of f times the integral of g. So just that will be useful. And then obviously also your integral of e to the at is 1 over a e to the at. So we use these quite often in most of these transformations. So let's look at if f is simply a constant, so it's not a function of time. If f is just a constant, then the Laplace transform of the constant, of course, it's like that. And then if you integrate this, this is integrating this in time. So s is a constant, so this becomes minus 1 over s e to the minus st. And so this k you can also take out as a constant. So k over s e to the minus st, and your limits, of course, not to infinity. So at infinity, this is going to be e to the minus infinity, which we know is 0. And so it's 0 minus, and then minus k over s at 0. So at 0, so remember this is in the variable time. So when t equals 0, this becomes a 1. So it's minus minus k over s. So the Laplace transform of a constant is the same constant divided by s. Okay, that's one property. And then if you have the Heaviside function, so this is a simple discontinuity function. It's saying that your Heaviside function looks like this. If this is 0, then the Heaviside function is 0 up to 0, and then after 0, it's a 1, right? So that's simply the Heaviside function. So the Heaviside function, if you apply it in Laplace here, then simply it's going to be 1 after t being greater than or equal to 0. So if we are integrating from 0 to infinity, which is what we integrate over in Laplace transform, then the function simply becomes a 1. And then if you integrate that, then that's 1 over s. So Laplace transform of Heaviside function is 1 over s. Then the rectangular pulse function. So that's if you have here's t equals 0, and then if you have another time tw, I think it is used there. then I think it's 1 here, and then it's 0 there, and it's 0 there. So for a short while, this function is on 1, and that's between 0 and tw. So yeah, well, yeah, we're saying k here. Okay, so it's k, not 1. So between 0 and tw, it's k. And then if you apply that here, that means we don't have to integrate all the way to infinity. Our function is actually 0 after tw. So we can say then we can simplify this integral. We don't need to integrate after tw. So we change the upper limit to tw, and then and so between 0 and tw, this function is k. And so if you stick that in there, now you don't have e to the minus infinity. You've got e to the minus stw. So you have to keep that upper limit, and then you have minus the ks e to the minus s times 0 here. So that part is there where this e to the minus st is a 1. And so it looks like this. So for your rectangular pulse function, it looks like this. Notice here, these are two discontinuous functions, Heaviside function and rectangular pulse. These are discontinuous functions, but the Laplace transformation is a continuous function. So, and you may say, well, that has to do because you've got a limit that's set in from 0. That's all true, but still, it is a continuous function, which is quite a useful property to have. You've got discontinuous functions that are continuous. Then the pulse function also, the Dirac delta function, which we saw a couple of times in residence time distribution, right? Remember, this one is at 0, it's going off weirdly to some value, which is not 1 or anything. It's going off to infinity. And then to the right of 0, it's 0. And to the left of 0, it's also 0. And it's going off to infinity here in such a way that the area under the single point is a 1. So it's quite an amazing function. The whole area is concentrated into one instant at 0. And that property applies. If you integrate under the function, you get a 1 under that single point where it's not 0. Okay, so if you apply Dirac delta, yeah, it has these properties. So it can also filter out specific values like that. So if you apply Dirac delta, Laplace transformation of that, then yeah, using, let's see which property, I guess this one, you are Dirac deltaing this function, and what you'll get out is the function here evaluated at the offset. So there's no offset here. So it's e to the minus st at t equals 0, which is a 1. So again, a function which is quite discontinuous now is a nice and easy representation. So that's part of why Laplace transform is so effective. Okay, then the ramp function. So if simply your time representation looks like this, if from t equals 0, it's just going straight up like that. If you apply it here, then let's say it's going up at a gradient k. So it's kt e to the minus st. And here you've got the product of two time functions integrated in time. So you have to use that integration by parts. And so let's let this be the function f. So you leave f alone and integrate this other part, which turns out to be 1 over s e to the minus st. So you've got the minus 1 over s here, and then e to the minus st, and you're going from 0 to infinity. And then here in the second part, you take f dashed, so the derivative of f here, which is k, so you've got a k, and then the integral of this part, which is going to be minus 1 over s e to the minus st. So where's the minus 1 over s here? Yeah, so it looks like there's an error that 1 over s somehow, did it really? I didn't think I had any errors here. So that's the integral of e to the minus st. Yeah, there's definitely a missing 1 over s here. And I see here now it's magically here. So it was so just there's an error here. Please correct in the notes. There's a missing 1/s. Oh, I see. I haven't integrated here yet. I've just written it as the integral of this. So we haven't integrated this as yet. Now when we integrate that, it's 1/s here. For the first part, you've got e to the minus infinity here. So that part will be 0. And then you've got 0. So t equals 0 there. So you are 0 minus 0, basically. So this part is just a 0. So forget about that. And then left over here, we've done the integration. We've got the 1/s. And then we have to integrate again still. And so it's going to be minus 1/s squared and then times k. And then you've got e to the minus st between 0 and infinity. So again, at infinity, that's a 0, and at 0, that's a 1. So we are left with k over s squared. So for the ramp function, it's k over s squared. For the exponential, e to the kt, so Laplace transform of that is, of course, like this. And then if you multiply them together, the common times, you can group together k minus s in here, or rather, why is it minus here? I guess this is supposed to be a minus. So please correct this error here. This should be a minus here and a minus here. Then it's e to the minus s plus k. And then if you integrate this, it's 1/s plus k, and then e to the minus s plus, and so you get that. Okay, now the first order derivative. So here's where it gets a little bit more interesting. So you now want the Laplace transform of a derivative of f. Right, so this is why this becomes so valuable now, because we are able to get rid of derivatives and actually, well, okay, let's not get ahead of ourselves. Let's do it, and then we'll see the rest of it. So Laplace transform of df dt. So you can write the df dt in there, and then you can use integration by parts. And here we are going to let this first part be the f and this part be the g, or I used a and b, I guess, because we have the f there. So there's the a, so we know we remove the a, so we just write the a out, so e to the minus st, and then for the second part we write the integral of that. So the integral of the derivative of a function is the function itself, and now we have to, the integration is on limits, not to infinity. So that's the first part. And then the second part, we take the derivative, so f dash, so the derivative, that's going to be minus s times e to the minus st, and there was a minus there, so this is plus s e to the minus st, and then you've got the integral of this, so that's f there. Notice this e to the minus st, that's, of course, we had to keep this part from a inside here. So now you've got this integral, and okay, let's deal with this first part here. So e to the minus st at infinity, e to the minus infinity, that's a 0. So we zero out the upper limit, minus, and then the lower limit at 0, this is e to the 0, which is a 1. So that's ft. And here t equals 0. So it's minus f at 0, right? So this first part, we've got a minus f at 0 here. And then for the second part, we can't actually simplify this further because we don't know f, right? So this one is a bit more abstract, right? It's the derivative of some unknown function. So without knowing this function, we can't really simplify this any further. But what we can say is that, well, if you look at this thing, this is nothing but the Laplace transform of some function f. In other words, we can identify y dashed. We can say we know y is the Laplace transform of the derivative. Let y dashed be the Laplace transform of the function, not the derivative of the function itself, right? And so that's what we leave it as. We say the Laplace transform of a derivative of a function is s times the Laplace transform of the function itself minus that function evaluated at t equals 0. Right, so this is not a direct Laplace transform. This is a relationship for a derivative. And you'll see this is hugely useful. Right, higher order derivatives, you can show repeatedly. If you apply that repeatedly, then you can keep reducing the order, and you can show that that the Laplace transform of a higher order derivative looks like this. And you can do it for the nth order derivative and so on. We might come back to this, but I want to stick for now on the first order because we'll use that just now. For the trig ratios, you can do it as well. I just want to keep with that derivative one and show an example. Okay, so here's an example. So let's say we've got this ODE and we want to solve this ODE, right? And it's not a very difficult ODE. We could do it. It's not homogeneous, so it's not as easy, but we can solve this with a bit of work. Now we want to see with Laplace transformation, there's actually almost no work to do. So here's our here's our equation, and we have an initial condition. So initially, y had a value of 2. So let's just Laplace transform this thing now. So we Laplace transform each term in this equation. So we know for the derivative, the Laplace transform of the derivative, it's equal to this thing. So it's going to be this times 2. And then we want the Laplace transform of y. We are because Laplace transform is a linear operator, we can just take the 3 out as a factor and just look for the Laplace transform of y itself. And then we also have to Laplace transform this 4. So it's the Laplace transform of a constant, which we know is constant over s. Right, so we apply a Laplace transform to each of the terms there. And so you can see clearly then that the first term is going to be 2, right? We know the factor of 2 has to be there. And then it's s times the Laplace transformation. So we are calling here y the Laplace transformation, and then minus lowercase y at 0. And we've defined lowercase y at 0 to be 2. So your initial condition, we just use the initial condition there, right? So in other words, this thing. Right, so once more, capital Y is your Laplace transformed version of Y. And so when we rewrite this, the Laplace transformed version of Y, so S times that minus the initial condition 2 there. And then for the second term, Laplace transform of Y itself is Y. And then Laplace transform of a constant is the constant over S. So that's the equation there. So it's a simple polynomial. And so in this equation, you can see you've got y in these two terms. And so you can group out a y. You've got 2s times y here, so 2s, and then 3y, so plus 3. So there's your y grouped out. And there is a leftover minus 4 here. So you're going to take that minus 4 across to this side. And so you've got 4 over s plus 4. Right, so that's the equation you have here. And then you can group out, so you group out 1 over s here. And because there's no s here, then you have to multiply by an s. And so you've got 4s there. And so you can say y equals this thing divided by this thing, right? So 4s plus 4 divided by s, and then divided by this, right? And you can simplify this a bit further. You can divide by 4 on the top. So divide by 4, divide by 4, and it looks like this, right? And now what we have available to us is a large table of Laplace transformations. So here on page 11, you've got all these Laplace transforms, and you can simply look up for a given Laplace transformation. Let's try and find it. I guess we could use this one. So you can look at your equation and look up the solution. So this is the time version of this Laplace transformation. So you look up on this table, the time function, and you have to figure out what the equivalent values are. So in the equation we need to figure out what B1, B2, B3 are. And then we use those numbers in here, and then that will give us the time solution. So where was this? So yeah, so that was the one. So we said B1, B2, B3. If you compare that with here, you've got those values for the B's. You do have to keep the 2 out and multiply the 2 by the solution. That's fine. But there's your time solution. Right, so you can, you see what's happened here is we were in the time domain. We transformed into the Laplace domain. We did a little bit of algebra and we got an expression for y, and then we inverse Laplace transformed back into the time domain. So that's what you can do for integration. If you stay in the time domain, the equation might be much harder to solve. It turns out that in this example, we could have solved it in the time domain. It would have been a bit extra work, but you could solve this in the time domain. There are other problems that are much, much harder to solve if you stay in the same domain. What you have now is a kind of alternate world that you can go into. So you can go into this S world, right? The Laplace world, where you have extra relationships available. So you can do things that are that feel kind of illegal. You can do things in the Laplace domain that you can't do in the time domain. And you can then get a form in S, and then you can easily transform back to the time domain. So that's what's happened here. So I wanted to look at this because it starts to give you the clue about why this is so valuable for controls, right? We have some idea about how to look at a plane of possibilities now, but we still don't know how to analyze it. Now we are going to look at features of that plane in the Laplace sense, and we'll be able to find relationships and do analysis that we could never dream of doing in the time domain. Okay, then let's just go back and see. I skipped over a couple of things here. I think it's fine. Maybe you can just go ahead and read up on these other things. This whole section is just revision anyway. I may come back to these things when we actually use these types of relationships, unless anyone wants me to go through any of these things right now. Okay, so Laplace transformations, and here's your transformation table. Time domain on the left, Laplace domain on the right. So we are going to transform into the Laplace domain, do our operations, and then translate back into the time domain. That's if you are solving differential equations. When we are doing our controls analysis, we won't necessarily come back to the time domain. So we looked at this. Yeah, if you have high order ODEs, you see this is an even better example. You know, if you were to try to think of solving this, well, there is a simplish way to do this if you just do order reduction. But anyway, this looks like a complicated equation that's hard to do in the time domain. But if you follow this example, you'll see it's very easy to translate it to the Laplace domain, and you can solve this problem very, very easily. Okay. And more general comments on Laplace inversion. Okay, so work through these notes carefully and make sure you can do Laplace transformation well. Now, those parts cover the for your tutorial. It covers the first, but in your tutorial, you've got, so we talked about all this stuff. Then your revision question 1, that's just being able to show you can do develop an unsteady state model. Your question 2, that's just showing you can do your Laplace transformations, so be able to do these. And the actual tutorial question is here. So in fact, we'll work through this first question. So the first question says, you've got this this reactor. So you have a reactor, so it's a CSTR, and it's a first order reaction. And let's see if, I guess another thing you should say is that the volume is constant. If the volume is constant, then you definitely get this equation, right? So hopefully you remember that from the reactors course. So you've got this equation that governs the rate of change of concentration in the reactor. And you also have the initial concentration in the reactor. And just be careful, you've got right the distinction between the inlet flow rate and the initial concentration. So that's the concentration in the stream going into the reactor, and that's the concentration in the reactor initially. So what we want to do here is rewrite this for the purpose of controls. Now, in controls, we have to identify what variable is going to affect the control. So here, CA in, that's how we are going to try to create control. And CA is the variable we are trying to control. So in the reactor, there's some concentration. We want to control that concentration. Flowing into the reactor is that. So that's what we want to change to maintain this control. Now, this equation is not so easy to use as it is, right? We want to translate this equation. We want to be able to translate this equation so that we have a relationship between the concentration and the control variable. So, excuse me. So let's just write out what we mean here. So we've got some equation like this. Dy dt is some function of the state y and the manipulated variable u. Now we would like to figure out a form that looks like this. We want y equals g times u, where y is the Laplace version of y, and u is the Laplace version of u. And in a way, you have to take this on faith for now, that if you can do this, if you are able to create a function like this one, then we can do all kinds of analysis, right? The moment we can get it to this form, a tremendous amount of analysis is available to us. So once more, we start out with this equation. This is what we can understand, right? From our mass and energy and momentum balances, we can always develop an equation like this. We want to take the same equation and translate it into this form. And this nice form is friendly to doing analysis. So let's see how we can do that for this situation. Now, there's a couple of problems with having it, with having this form of equation to begin with, right? If you have an equation like this, you see, you've got, first of all, an initial condition which is not zero. So if you have this non-zero initial condition, you are going to struggle. I should go back to the notes. You are going to struggle with having this extra term. You are going to struggle with having this extra bit floating around, which you won't be able to get rid of. Here, this. So we really want to get rid of this. We want this F0 to be 0. And obviously, in the physical situation, we can't do that. The problem as it is what it is, right? If you in your real world, this is not 0, you can't change that. But we want to find a way to transform this set of equations into an equivalent form, which is friendlier to being translated to Laplace transforms. So we're actually looking to create a transformation for another transformation. Okay, so please keep track of the layers here. We want to first translate the time problem into another time problem before we can do Laplace transform. So that's what we're doing at the moment. So I've got all this shown in detail in my solution. So let's let's look at how we translate that. See, lots of pages of solutions here. Hope you're going to read all this. It took me forever to write all this. So anyway, so here's how we do the translation. We are going to propose what we call deviation variables. And in a way, this keeps the character of what we're trying to do. We're not trying to work directly on C, because that doesn't matter to us for control. What matters for control is deviation. How much are we going away from steady state? So we are going to create this variable y, and we are going to consider this to be how far we are away from a steady state. One steady state we know about is the initial steady state. So one of the things we require is that the system was at steady state in the beginning. So initially, right, and it doesn't exactly say that here, right, but to do this, you have to assume the system was initially at steady state, right? Afterwards, there was disturbance because CAN was changing, but initially you had to be at steady state. So CA naught is the initial value of the concentration in the reactor, but it's also a steady state that was initially there. So you need to state that up front. So you've got an initial steady state, and y is defined as the departure away from that initial steady state. There may be other steady states, but we are defining y in terms of that initial steady states. So that's y, that's the deviation. And then the other variable of interest is our control, right? We are controlling this process through the inlet concentration. And so we have to consider that also as a deviation variable. And we know that CA in is changing generally in time. And we are identifying, again, initially, there was some value for CA in. And at that value of CA in, right, that initial value, we know we were at steady state. So this is kind of a value of CA in. It's not zero, but it's some value such that the system was at steady state when it was that value. So the departure from that initial inlet steady concentration, so the difference between your current inlet concentration and that initial one, that we call U. So these are both deviations. Y is the deviation in the reactor from its initial steady state, and U is the deviation of the inlet concentration away from its initial, which was steady value, right? So we've got that. Now, what we do is expand this equation such that we have all those terms in there. And we do that by adding and subtracting. And in fact, what I need to do then is show that a bit. So let's say now we wanted to create the CA in. So so if you want CA in, if you want to be able to say CA in minus CA in naught, then we have to add and subtract that. So we're going to do that here. So let's say we just put it in here. So we're going to say CA in naught. So we're adding CA in naught over tau. And then to keep this equation valid, you have to subtract it as well, right? So you're adding and subtracting the same number. So we know this equation is still valid. And then we've got CA here and CA here. So we have to add and so we want to make the departure from steady state. So we're going to do this again here. So we're going to say plus. And so we're going to say CA over tau here minus CA over tau there. And then this stuff, CA naught, because we want to get the departure. And then we want this one. So we're going to say again, plus CA naught minus. Okay, so I hope you agree. This is the same equation as we saw above. We've just added and subtracted the same numbers to it. And now we are going to regroup here. So we can move this CA naught in next to this CA in. So you make this term, and then you've got this minus CA over tau, and then you group that with this CA naught over tau. And then you've got, I guess, this one, CA naught over tau. And you're going to group this with this CA in naught over tau here. And then, and so you see, you regroup all these. So wherever you see a CA in, you want to group that with a minus CA in naught. And wherever you see a CA, you want to group that with a minus CA naught. So that's all we've done there. It's just we've just shuffled this equation a bit to get the right differences in concentration here. So when you look at this now, you can see this is going to be a Y, right? Sorry, not Y, a U. So that's U. Then CA minus CA naught, that's Y. And then this is U. Sorry, not U. This is something else, actually. Let's see what that turns out to be. And then you've got, this is Y, and then you've got that bit left over. Okay, so there is still some stuff to get rid of, right? Now, let's see here. We notice also, just in terms of this left-hand side, remember if we had rewritten this, if we look at the derivative of CA minus CA naught, right? CA naught is that initial steady value. So the derivative of this in time, it's a constant anyway, so that's going to be a 0. So we can identify that dCA dt is identical to dy dt, okay? So that's there. So we can make some substitutions now for u and y. So this one is clearly a u. This one is clearly a y. And then here you've got a y again. And then here, this is CA naught minus CA in naught. That's not y or u, right? This is not inlet. And so this you have to keep, and also this you have to keep. These parts didn't cancel out. Okay, now, so that's all well and good. We've got some u's and some y's. Now let's see how we can get rid of this part. Now we have said that initially the system was at steady state, right? So when t equals 0, this whole thing was at steady state. And of course, when t equals 0, this is equal to CA naught. So dCA dt at t equals naught equal, right, that's equal to naught. And then we know CA is CA naught then. And so you can write that in for CA naught. And so you can see that this whole thing here is going to be a 0. So we have to use that steady state initial condition to get rid of this part, right? And now that we've done all that, we've got the equation in this form written in terms of deviation variables. And notice here that our initial condition is a 0 now, right? So we've transformed into a different set of equations, also in time, but with a 0 initial condition. Okay, and now if we Laplace transform this, remember if you Laplace transform this side, you're going to get sy, and now you don't have to worry about minus y at 0. We know that's 0, so it's simply sy over here. And then this stuff here, obviously that's u and that's y, so u and y, and then minus ky. Okay, so now the equation is Laplace transformed. And then we can group out our y. So you've got y here and y here and y there. And you do have a non-y. That's important if you want to solve for y. So you group all the y's together here, and then the leftover stuff is this u over tau. And then you can rewrite this in the form that we were looking for. So remember, we wanted y equals g times u. So if you look at this equation now, G is equal to 1 over tau divided by this thing, 1 over tau divided by that. Right, so now we have this, what's called a transfer function. So that's what we're looking for. So those are the questions in tutorial 1. So we've just worked through this question 1 here. And you'll see question 2, question 3, these are all of that type, right? So you've got all these situations, you want to develop the time equivalent of this, and then you want to find the Laplace transfer function. So you want to find the G function so that you get this nice form. So that's what I wanted to cover for today. Maybe we should talk about what parts are you should actually submit for the tutorial, but before we discuss such mundane things, maybe any questions or comments there? Okay, so I'll take that to mean we are all completely happy with that and no questions there. It's all clear. So that's what you need to do, right? So you transform into a different set of time equations that have 0 for the initial condition, and then you do a little bit of algebra and you get a nice Laplace transformation. We can talk a bit further about this example 1. You can see here, so it says, how does the equation look when you use a PID controller? That's a little bit beyond where we are right now. I mean, we've just had this first contact session, so and then maybe we'll just have a quick look. But the interesting one is if we use a step input of m, right? In other words, if your inlet concentration goes up by a factor of m, how does Ca change with time? Now, a question like this would be quite daunting, right? If you were to just look at this from the perspective of time, right? It's a little bit intimidating because you can see here your Ca in is going to change with time, and it's a step function, which means it's there's a discontinuity for this, and you still have to integrate this whole thing and then figure out how that's going to change things. So it's quite a daunting problem, but now with your incredible power of Laplace transformation, you have this transfer function. You've got this nice relationship between y and u, which is here, right? So g is this function. So y equals g times u. So you can take your transfer function and say, well, my u it's going to go through a step. Now remember earlier we looked at the step function. We said when you use a step function, your Laplace transformation is going to be the constant divided by s. So now, so far we've been doing it in the abstract. We just said y and u. We didn't worry about what forms those were. We didn't say anything about how Ca in was changing with time. We knew it was a time function, but we didn't know what form it had. Now we are saying it's a step function. So if it's a step function, if you look in those, what we did earlier, we said the step function is m over s. So now that it's m over s, we can see that y has this relationship with s. Now there's nothing mysterious here, right? Before it was a bit mysterious. We didn't know what was behind this u. But now we know what u is. It's a step, so it's m over s. M is a constant, and then tau and k are also constants. So now everything is fully specified here. There's only s, which is the variable, and a couple of constants. So now we can just go over, we can trundle over to that table of transformations and just look up if I have a function constant over s plus constant divided by s, right? So if you, where's that thing? Yeah. Right, so if you look for the same form of equation, So S, you might have to do the product of two. And that's something we need to talk about. Product of two is also easy with Laplace transform. But I guess it's one of these. So anyway, you look up the transfer function and you just figure out B1, B2, B3, and then that gives you the solution. And that's the solution there. So if you have a step in M, then this is how it's going to change in time. Actually, it seems, I think there's a missing M somewhere here. I seem to have forgotten the M. I think this whole thing needs to be multiplied by M. But anyway, you've got your time function here. So that's how easy this makes it. You can, so besides Laplace transformation, just this transfer function, you see, now that you have extracted the transfer function itself, you can very easily think about, if I apply a certain control strategy using a step function, using something else, how is my system going to respond? So that's the beauty of transfer functions. They make it very easy for us to consider the impact of a control strategy on an output variable. Okay, so that's what I wanted to cover today. Any questions or comments there? Then in terms of what is submittable, what's the right word? In terms of what you have to hand in for this tutorial, I guess, do that first revision question, and then just pick a question from each of these. So you can do one out of each of these 4 questions here. And then I guess choose any 2 in this. So that's what's due for Monday. Obviously, the more practice you get, the better. So try and do all, but submit at least 2 of the questions from this part. Okay, does that sound reasonable? Okay, I'll take that as a deafening yes. Okay. All right, I guess that's it. See you in the next one.